Hello, so this is the first time, so this is going to be my first edit of M33, so let's get going. First of all, we're going to be doing LRGB, just because I think that's just easier, and then we'll get to the narrowband stuff. That's gotta pull it up, LRGB, so the way I have my files organized is by the ways I'm going to go about it. So LRGB is where my LRGB data, and the combined data is where my narrowband data is. So the reason I did it like this was because I wanted to make sure that everything was in a good spot, so I knew where it was when I first started editing. So you may notice that there are these TIFF files, which are not, normal FITS files. The reason I did it as a TIFF was because when I originally started this project, I did it as TIFF because I had Photoshop instead of Pixinsight. But after testing it, there's no difference between FITS and like a ZIF file, other than the fact that there is no data built in. So that's just kind of the unfortunate part, but I didn't really see a problem with editing, so oh well. With LRGB, I did do a ZIF because I needed the Astro data to be built in, so I organized them by B1, G1, L1, R1. That's where all my data is. So now we can get rid of the weight images. So here we are. So when we do an initial stretch, we have our beautiful data. This is only I think 2 hours. So what I am going to do is going to be undoing the drizzle with the resample, because I realized that Noise X does not like big images, especially in narrowband where the data is kind of blotchy in the first place, especially with the continuum subtraction. It does not like it, so that's unfortunate. Another problem with my data is that we were out of focus a little bit, but with BlurX it seemed to fix it, and honestly it doesn't look too bad. It's just that if you zoom in really close, yeah, there's an obvious difference between green and blue, but it'll be alright. With some simple BlurX, we can fix this. I like scrolling around the data, see what we got. What I am going to do is, first off, I'm going to just do a quick BlurX on all of these. Just going to keep the settings kind of the same, because we don't really need it too big. One problem though is that it does kind of over sharpen the stars inside of M33, which is not cool, but oh well. So now our data is complete, and here's what I mean. So the stars kind of get elongated. I'm thinking what's going on is it's thinking it's a nebula, and so it's just kind of elongating it. It's alright though. The core looks extremely cool, but yeah, it doesn't look too great. So this will, these stars will also be a problem when we do a continuum subtraction, because it'll be black splotches. I will fix that in Photoshop, but with just some simple clone stamping and all that. But yeah, we're just going to do it to the rest of these images now, just to make the stars the same size, which will make star aligning and combining the images a lot easier. And on red, it's a lot easier to tell that these are actually stars. The one thing that is nice though is that we're not focusing on the detail of LRGB. Well, RGB, we're focusing on the detail from the luminance, and luminance was still in focus, so we're going to be alright. Mostly. Just takes a minute. So once we are done with BlurXing and then combining these images, we're going to be doing an SPCC, a spectrographic color calibration, I think it's called. Or is it? No, I think it's spectrophotometric color calibration. Basically using the spectra of stars to get the white balance correct, because I'll show you what it looks like without and with. There we go. Here's green. Then here's our L. L is like, I can tell it's like just a teensy bit out of focus. That's just because when I was taking it, I was asleep. I should have really just gone out during. So this is World 2 skies. So I only needed a few hours of data. So I was like, oh, I can just sleep through this. Because I never really had an issue with it going out of focus, but the temperature did change quite a bit. So I took my RLGB. I really should have just refocused during, I think, G. I think that would have been a better idea, because G and B are along the same focal plane. But oh well, we'll work with what we have. It'll be okay. This also gave me the inspiration to finally get a autofocuser for my Newtonian telescope, because that is a huge issue, especially in these upcoming freezing temperatures. Yeah, there we go. So these look a lot more like stars, so I think we'll be okay. Now, we're going to be... We don't need a blur X anymore. Well, we'll need it a little later for the narrowband data. But what we can do is we can go into... Where is it? LRGB. Wait, actually, I'm stupid. I have all of my things right here. So, there it is, LRGB. L R. So I am gonna rename these. I'll throw away G in a minute, but with LRGB, I'm going to rename them because of my continuum subtraction equation. It relies on it just being a single R, G, and B letter, which makes it easier. So the reason we're going to do an SPCC is because when we stretch the image, it looks like that. I mean, it looks cool. We lose a lot of... It's just not looking too hot. So instead, what we're going to do is hop on over to spectrophotometric color calibration. That is a long word. So we have everything here. I'm just going to make sure that our... I think we're good. Yeah, no, it's only for figuring out where we're at in the sky with the image solver. That's when we need to put in our what's it called? Focal length and all that. Luckily with the red cat, we don't need to do that. And there we go. There's all of our data. So it looks pretty bland. That's okay. So here, I'm just gonna close these out because we don't need them for now. I'll rename them later. I'm just gonna work on only LRGB for now. Then we'll move on. Alright, so we have pretty sweet looking data. I think we can do another stretch, and that'll fix it up a little bit. Nope. One of the problems we do have, though, is the background is terrible. So, I'm just going to resample real quick, just to make it easy. Image 09, 50. That's okay. We don't need the astrometric solution anymore, since we already did it. Alright, sweet. And that also makes our signal to noise ratio a lot better. So now we can allow a lot more. There's even a couple little cool galaxies in the background. This is just with the red cat too, so pretty excited about that. Just gotta get rid of the the background isn't horrible, but we are gonna fix it a little bit. There's all of our stars. Yeah, it's pretty sick. So then we can go into DVE. Make sure it's selected. Let's set tolerance to 10. So I learned this from Adam Block's tutorial. Set the sample radius to 20. Samples per row, also 20. That way we get just an easier solution. It also makes it easier to click. Mainly what you're doing here is just moving it away from the galaxy and deleting the ones that are inside. So like, this one didn't get selected. That's okay. So basically, you want all these points outside of the galaxy. You don't want any inside, because if they are inside, then that means you're going to have a very bad day. Now, where's that? Here, we can change it up so it's easier to tell. There it is. I almost missed a couple. So we want it away from these tidal streams a little bit. It did an alright job. I forgot. I need to... Oh. Should have not trusted it. Yeah, no, we need to redo that. I forgot, so I need to take it away from the... what's it called? So these splotches right here, they kind of ruin the image, and we can't really crop yet, so I have to get rid of them. We'll just move them. So, yeah, this process is also kind of soothing for me, so it doesn't matter too much. Yeah, mostly. There's a few spots where I forgot. I think we can actually just do it again. Would that work? Forgot about that one. Yeah, that did it. Okay. Cool. Alright, so that cleaned up our background a lot better. We just have this little bit of green, but I think we're going to exclude that and only include like this much of the galaxy. Just going to add back our stars. I also will rename this to RGB. Let's make it easier. Okay. So now that we're done with that, one thing that is my goal for this project was every single time I saw an image of the Triangulum galaxy with like narrowband or even without narrowband, NGC 604, one of the biggest nebula in the entire galaxy, is always blown out, which always kind of caught me. Like, it always like made me like, I don't really know the word for it. I just didn't like when it was blown out. So my big goal for this one is to not let that happen. I have a few ideas of how I'm going to do that. I think with some masks I can make it work. Just gotta be very, very careful how we stretch. So I'm going to use GHS. I think we can put a black point. There you go. So black point. Oh. Generalized hyperbolic. Send to symmetry point. Unstretch. Re-stretch. So there's our problem, obviously. If we stretch it too much, it looks terrible. So we're just going to do a little bit of stretch. I'm going to create a little preview here, just to make sure that this nebula is being blown out. It already is. So we're just going to put a local intensity on there. It's already doing wonders. For another symmetry point, right there. We'll bump it up a little bit. Make sure that this isn't being blown out again. It is. There we go. That looks good for now. Okay. So now NGC 604 is not being blown out. Neither is the core. So we can put on some curves now. So I always like to bump up the saturation, because then that shows the most amount. What is that? A little bit of green in there. I think we'll do a SPCC to get rid of. No, sorry, a SCNR to get rid of the green in this image. So I don't like how blue the galaxy is. Alright, there we go. Looks pretty sweet. Then we'll put on an SCNR to get rid of all that green. Yeah, definitely don't want your image looking like that. Looks pretty alright. There's a lot of color noise, obviously, but we can get rid of that. So when we do a SCNR, it will kind of get rid of a lot of the background, which is okay. The background is obviously red. Make sure we're not clipping anything. Okay. Yeah, we're still okay. There's just a little too much red. Kind of want just the core. I think that's pretty good. Okay. I think that looks pretty alright. Yeah, I definitely like that color a lot better. I think we will make these stars a lot less saturated. Yeah, I definitely love that color. That's pretty sweet. So definitely got to get rid of some of that noise. So there's not too much. I don't want to overdo it, because if we do the default value of 90, it's going to be too much. and it might get rid of like some of this like stars and stuff. I do like a little bit of noise just to keep it, I guess, real. I don't know the right word for it, but you'll see what I mean. Yeah, like just a little too much. It makes things kind of watery, which isn't exactly what I'm going for. So what I say is we bring it down to, I'd say 0.4, maybe 0.5, just do 0.5. Just so it gets the majority of the noise, and then keeps the detail. I think that's good. That's a lot better. Just still a little noisy, but it'll live. Yeah, see what I mean? The stars are a lot nicer just because of the luminance. I think that looks pretty sweet. Yeah. That's kind of annoying, but again, I already checked the O3 data. We can just crop it like this. There'll be no issues. Okay. So I think that is our LRGB image right there. Pretty sweet, honestly. Oh, almost forgot. Gotta drop the stars a little bit. Vibrance. Because I mean, the star colors are nice, but I don't want them so colorful. That's a little overbearing. There we go. Sorry, I was just scrolling in just to make sure it has everything. Let's drop in the curve. We're just going to focus on these bright stars in the middle. Oh. I think that looks a lot better. I think that looks a lot better. I forgot to lower down the blue. If we just, is there a way we can just drop it? Nope. Color. We'll see how weird it looks. And then we can always drop it back if we want to. Yeah, that looks a lot better. Yeah. Didn't really change the stars on the inside. I just didn't want that overbearing, like, red glow from these stars. Okay. I think that's pretty much it. I think maybe we can lower down the blues a little bit. There we go. Is that green? Nope, that's black. Okay. Well, a darkish gray. That looks a lot cooler. I don't think the blues are varying in the galaxy. I think that looks pretty sweet. I like the browns in the dust lanes. So it's pretty much staying the same. So that's good. Okay. Let me just stare at this for a minute. Yeah. I think that looks pretty good. The core is nice. This isn't blown out. I think we can call this a finished L image. So what I'm going to do is I'm going to save this project as M33. Okay, there we go. So there's our RGB image. And now we're going to move on to narrowband. So first off, I'm going to move on to hydrogen. Before I even stretch it, I'm just going to do a quick blur X. Alright, so now that's done. There's our data, by the way. Let's get blur X out of here. So this is what I mean also. NGC604 is just so overbearing in hydrogen. It can be seen in like 1 second exposures when I was doing plate solving. So yeah, it's pretty wild. There's also a few little dots around that are new and have not been spotted before in a catalog before. I'll talk about those in a little while. So usually ABE, well actually before I do that I should star line. So ABE usually takes care of the what's it called? The background for hydrogen because it's very linear. I saw hydrogen during like the fuller moons, which I know wasn't a great idea, but like I don't know, it looked alright in the end. Then I shot oxygen during no full moon. I'm in a Bortle 6 already, so I knew it wasn't going to be too great. Yes. Alright, now that that's gone, we can rename this to H for hydrogen. Then we can remove this star line. Automatic background extractor. Subtraction. Bop, bop, bop. Yep. There we go. Got it pretty good. Yep, didn't create any black spots. So these little black spots right here that I notice are because of what's it called? Dust mode. So when the moon was projecting on for like a single frame, there was a dust mote that was being projected onto the lens, and flats couldn't take care of it because it was a different lighting condition. So it's fine. We'll be okay. So, excuse me. A few things to know about this data. Number one, I noticed this long line of hydrogen. So I'm going to see actually. So this might actually be a star forming region. I think so because I see a couple of new stars. Actually, hold up. Let's put up RGB. Yeah, no, that's a star forming region. That's pretty cool. And then the brightest point, I call it M33's Thor's helmet because to me it looks like an looks like the Thor's helmet with like the little top and then the horns. It's much more apparent than oxygen. But yeah, there's cool blue stars around. This bubble intrigued me. I still want to know if this is actually a supernova remnant or if this is just like a bubble of hydrogen. Because there's also another one right here. And I'll talk about that in a little bit when I finish the image. I don't know what that is. Again, I want to research all of this because it just looks so cool. Anyways, let's get on to continuum subtraction. So, this is where it gets kind of complicated. We rename R. By the way, renaming, I should have mentioned this before. You double click to the left of to the name. The new identifier is R. That's my red. I guess while I'm at it, I will also name blue B. Oh no, BV B. Reason I do this is it just makes it simple when I do the equation. So I'll also link the video where I learned how to do the continuum subtraction because that video helped me a lot. So in this equation, we have the hydrogen minus the median times red median R. Actually, sorry, Q is the variable or the multiplier. So we have H minus the multiplier times red minus the median times R again. So what this will do is this will subtract the red from the hydrogen, and it'll make it a lot easier to see this. The reason we do this is because if you notice, there's like a little bit of this cast that goes outside of the just like the normal hydrogen. That is not hydrogen. That is the light leakage of the white light of the galaxy pouring into the red, which is not what we want. So I create a preview by selecting new preview mode, clicking the select button, then just dragging it. I just like dragging it over the entirety of N33, just makes it easy. I should also mention the Q. If you go over to symbols in Pixel Math, Q equals 0.25. However, in my data, it will be somewhere around 0.075. This will just look a lot better. There we go. So if I were to keep it at 0.25, you're going to notice something really strange happen. Yeah, you do not want this. Whenever you're doing continuous subtraction, you don't want your data to be clipped because then it will completely ruin it. Let's say 0.75 is good because it gets rid of most of it. If we jump up to 8, I think that might be a little bit too much. Maybe. I think we'll be alright. These black splotches are stars that it didn't get rid of. I'll skip past it in the recording, but the way I'm going to get rid of these is just clone stamping very close. Not trying to fake data, just get very close to the star. So like this star, I can tell just by this little artifact here, is not part of the main hydrogen. So I would just click here and clone stamp the same radius of the star and then just blotch it in. Because I don't know if this is like an actual detail, so I'm just going to get rid of it very, very carefully. Things like these, I think Noise X will take care of, but like bigger stars like that, I'll have to get rid of manually. This, I actually don't even know. I think that would just be a star though. But yeah, I'll have to be very careful with how I remove the stars. But hydrogen is the easiest because these stars were almost the exact same as hydrogen. But yeah, this looks pretty sick. I love this wave of hydrogen. Just looks super cool. So there we go. Just import that. So that is our continuum subtracted hydrogen. And now what we can get to do, we're just going to close this because we're going to do it to oxygen as well. So you're going to resample. Because this was drizzled, and this just makes this SNR better. Now when we stretch it again, looks pretty wild. So here is that nebula again. That's much more brighter in oxygen, so I'll definitely show that. But yeah, I don't know, I just like scrolling through the data because this is 50 hours of hydrogen. Hydrogen. Super sweet. Alright, so yeah, no new nebulas or anything, so well, I'll talk about it a little later. But now we can get to do a generalized hyperbolic stretch on hydrogen. See, if we stretch it too much, it's just bad. Before we get too into it, this nebula in NGC 604, I don't want to blow out. So, again, just make a little white. Okay. Now again, we have to be careful because I don't want to blow that out. I think that's just barely cutting it for clipping the data. Yeah. I just found something out I didn't know about GHS. We're gonna go over here. Just gonna stretch. So that looks pretty sweet. Now NGC 604 is blown out. Make this a little leveled out. That looks pretty sweet. Yeah, I'd say so. Nothing's completely blown out. And everything is in detail, so I'd say that's pretty good. Same thing with Noise X, I'm only going to do it by 0.5 because we don't have too much going on. Then with a curves adjustment, we will bring out some of the data and leave some behind. I do notice that our background kind of sucks, so I will fix that. I think that'll look okay. Oh, that's another thing I wanted to mention. So in NGC 604, there's something really strange. There's always like these large strings, I guess I'll call them. I haven't noticed that before, so that was pretty sweet. I think that looks okay. I just wanted to get the background out. Oh, wait, oh yeah, we got it. Sweet. Alright. Let's see if ABE can get rid of the background again. Probably not. Oh, no, it actually did. Okay, sweet. So, I am gonna actually do this, like adding the hydrogen back in Photoshop, because I will show you what happens if I don't. So here we're going to create a little bit of a preview. I think this will be too much. Actually, yeah, we'll see. Associated. Oh, yeah, forgot it. So, yeah, a little bit too much. But you can see where all the hydrogen is. We'll set it to 0.5. So, I mean, yeah, it's pretty sweet. Don't like how much the red's glowing in here, though. There's also a bunch missing from this wave right here. So yeah, we're gonna be setting that to screen in Photoshop. So that's unfortunate, but we can work with it. So what I'm gonna do is I'm gonna save this as a TIFF, not a JPEG. TIFF file. We're gonna create a new folder, Astrodata Library. New folder. So we can set this to 16-bit because we aren't like trying to gain more out of our data than what's already there. If that makes sense. I would keep it to 32 if we were stretching it still, but we're practically done. I will also be creating a Who image. That'll be kind of off recording, so that's just simply combining the hydrogen as red and the blue and green as oxygen. So I'm not going to be keeping the recording on for that one. So here's oxygen. So M33 has barely had any oxygen data done to it. What it looks like. There's Thor's helmet. There's the bubble. There's the bell. And up here is MEU1, or McCollum Extragalactic Unknowns. So it's not an official catalog, but it's one I'm making because I would talk to Marcel Dreschler about this. I can't make this my own nebula. Like, I can't like put this on like a thing where I can just make it officially McCollum 1. So instead I'm creating my very own personal catalog. Same with this nebula, MEU2, and this one, MEU3. So what's really strange about these three, all three of them have a Wolf-Rayet star in the middle of them. I checked this on Simbad. I made sure to get all the coordinates right and all that. They all have, this one has a Wolf-Rayet star. So there was originally a study done on the Wolf-Rayet star density inside of M33. And all those stars were labeled, cataloged, and all that. What they didn't do was they didn't see the similarity between the nebulae and the relation between the nebulae and the Wolf-Rayet stars, which I wish they would have done, but that's okay. So these nebulae are extremely huge. I'd have to really, I think they're probably thousands of light years large. Like, or maybe even, I think an easier comparison would probably be like low thousands, high hundreds. This one's absolutely gargantuan in size. This one's the brightest, and then this one's the dimmest, and I wouldn't say the smallest, but it's pretty small. But yeah, I haven't found any others. I did notice there was a little bit of like striking going up and down. I talked to my friend Julian about this, and we kind of decided that this was satellite trails going up and down the image that were just kind of averaged out, but kind of stayed in the data as well. There's also this thin tail, or loop of oxygen going around this nebula. This nebula is particularly bright in oxygen. There's also the infinity loop of nebulae clusters. I always called this the anglerfish of M33 when I first found it in my first 5 hours of data. Which, if you go northward, or I guess this would be westward, because of the way it's oriented. There it is. There's also this nebula, which was just discovered a few months previous, and that was pretty sweet pulling that out. So, yeah, it's pretty cool. I actually don't know what that is. Let's figure it out. I'm gonna put before I do that, I'm gonna put a little bit of blur X on there. I started this project August 2nd. It is now November 4th? Yeah. Feels good finally being able to be done with this. I loved it, don't get me wrong, but it was painful. Yeah, Thor's helmet's crazy looking. This is like a clamshell looking nebula. There's a little bubble right there. It's very bright. Can you see in RGB data? NGC 604. Yeah, no other like planetary nebula or anything crazy like that. Not saying that was my goal, but that would have been cool to get at least a little bit. So we're just gonna do a quick star alignment here. Bye, oxygen. Oh. Let's do a little stretch here. And now it's aligned. So another thing with this nebula is it is there in hydrogen very faintly, but it is there. It's also in this nebula as well, but again, very, very faintly. And this nebula, which is the biggest and second brightest, very faintly there as well, with a little bit of a little buddy right here. It's pretty insane that this, when I found out this was real, like, that was super cool. Oh yeah, the Bell Nebula, extremely bright. So I guess we gotta do a little bit of a DBE on this. So what I gotta do is I gotta take away it all on StarX so I can do it easier. Yeah. Okay. Pretty sick looking data. Actually, just try to check if blue is pretty bad. I think blue is also bad with it, so we'll set that up in a minute. DBE, here we go. 10, 20, 20. Turn this to pink, hotter pink. Generate. So another thing is, the core is particularly bright in oxygen, which I found very strange. It was just something I didn't expect. Like, because it kind of reminded me of Andromeda's core. With how bright it is in hydrogen. I don't know about oxygen though. I think that's a project for next year. Wink, wink. But yeah, pretty sweet. Yay! Took care of it. The bad background is now taken away. So it just makes it easier to continuum subtract, which is nice because if you don't have a good background to continuum subtract, you're gonna be seeing a lot of weird things happen. Alright, so we don't need that. O plus O underscore stars. Drop it in. Sweet. Then for blue, we're going to do the same thing. I guess we don't need these stars anymore. Blue, we're going to do the same thing. Alright, so this background isn't too bad. Also, there's our satellite trail. We'll live with a little bit of a satellite trail. Dynamic background extraction tolerance 10. Sample radius 20. Samples per row also 20. Set it to pink. Bridge pink, make it easy. Subtraction, bop, bop, bop. Generate. Alright. Luckily, it stays away from the core and these brighter, stretched images, which is nice. Makes it easy. So this one's take away all those. Just want it to stick away from the galaxy itself. Press subtract. Also, by the way, there's some leftover amp glow that did not get taken out because of my 183 camera. Okay, but again, it didn't really need to take it out too much. It's going to be okay. Pixel math. Okay. So now that everything is extracted, we can now subtract. So, almost forgot to create a bits. Here we go. And that's what I mean. So, the star clusters really don't like playing with the oxygen data. Nor does it like playing with NGC604. However, what I think I can do with Photoshop's screen tool, I don't think it'll count the black spots. Pixinsight, when it adds it back with this narrowband feature, it does not like it. Also, now you can really tell. There's something there. There's something here too. Oh yeah, this is another thing. There's another one of these, like coming out of the nebula. I don't know what that is. I think what I'll do next year is, with my big scope, 8 inches, I'm going to spend the same amount of time, but just on NGC 604 at f4. I think that would be sweet, because that is a strange feature. Like, I don't know if it's real or not, but it looks pretty out against the noise. Same with... oh, actually, I don't know what all these are. Might be adding a couple to our catalog here. I'll have to figure that out later, though. Let's turn this down, though. I think it's a 0.2 would work. Maybe. Yeah, just a couple of these. I don't know. We're gonna have to start them after I'm done making this recording. Get a little bit of local intensity in there. Yeah, there's our satellite trail. I don't know if you can see it, but it's like up and down this way. I thought that was a supernova rim, and I got really excited when I first saw it. Okay, I think we're done with GHS. There's our nebula. just going to apply. So with oxygen, I'm going to apply a little bit harder because there's not much signal in oxygen. And again, this isn't really like an official image. Yeah, that might screw me up later. I think I'll create a little bit of a mask. Oxygen also has a wave up north of Thor's helmet. It's pretty sweet to see. Yeah, wow. Alright. I think we're ready to combine. Or do you? That might be new stuff. I'm not going to catalog every single little dot that like I don't see. That I see. The super bubbles already been cataloged. I wonder how many planets are in it. I wonder if that's a planetary nebula. Might be. It's stuck in the frame. So this too. But also this little guy. Oh my god, that bubble is so cool. Alright. I think we are done. It's a weird sentence to say. Okay. Hour into the recording, we finally got everything stretched out and done. It's 2:55 right now. I'm going to stop this recording and create a part 2 of me doing this in Photoshop. So what you can do, if you're a hardcore Pixinsight user, is you can use the adding narrowband script. This is the how you type it, by the way. Let me just get rid of the R. So it's $, so to add the hydrogen, it's $T plus I times parentheses H minus medium, parentheses H, parentheses, parentheses. By the way, you don't want to use a single RGBK expression. But then for green, there's not much green in hydrogen, so you can turn that into a $T. There is you can simulate adding hydrogen beta, and I always like adding like kind of pinkish nebula instead of just hard red. But you can always make that like just adding a little bit to it, and then this will look good. Then for symbols, I equals 2, and then just play around with that variable. For oxygen, turn this into just $T. So here, I'll show you what you do. So you want to turn this into just $T, and then for green, you'd want to make this the original hydrogen base. Instead of H, you want to replace that with O. And then same thing over here. So to show you what that would look like, that adds all the oxygen. It's kind of like a teal color. Always looks kind of bad that high up. But maybe if you do 0.4, it don't look that bad. Yeah. There's all your oxygen. It also makes the core extremely bright. Yeah, there it is. Super sweet looking.